Okay, so we're doing problem 14.
Yeah.
And let me share my screen.
Yeah, but will this class make so we'll make linear algebra a little easier by the time I'm done?
Yes, it definitely will. We've done a lot of things here. In terms of linear algebra, I think you learn like basics at least. Okay, so says the qubit is in state U or V, right? And we want to determine which state it is in by measuring it. If I share this screen, then it's not going to record the board. I guess I'll stop sharing the screen. And I think you can see the problem 14, and then we can solve it here. So you see a diagram similar to this on your
Yeah.
So you see a diagram similar to this on your question paper.
I'm looking.
And you have U right here and V is right here. Right? And then you have U perpendicular, which is at 90 degrees. So 90 degrees we refer to as with this. If something is 90 degrees, we write it like this.
Yeah.
Anyway. So if you want to measure something in a particular space, right, you take a dot product, isn't it?
Yeah.
So you take something like this. If you want to measure phi in terms of, let's say 1, you do something like this. The neat thing about this is if you had, let me make it bigger because it's not going to be visible there. If you have something like this and 1 existed here, 0 existed here, keep in mind that for now this works only when 1 and 0 have real coefficients. So basically, 1 and 0 must have real coefficients. In the sense, if you have a vector written as A0 plus B1, here A and B must be real. Only then this method works. Make sure this happens. So if you want to measure what the probability of any vector phi is in a particular axis. Let's say I want to measure the probability of phi in 0 axis, right? I just take the angle between them, theta. And since you take probabilities as this thing, right? 0 and phi, and then square it. This is your probability of phi existing in 0, right?
Of the phi existing 0 equal to the product of 0 and phi squared.
Yeah. So
okay. Is that 0 pu and then what's
this is not important right now. So you have, so I'm just trying to lay the groundwork of this problem.
Yeah.
Okay. So think of it this way. If you want to measure the probability of any vector in a given basis, you take the angle between them, you measure the cosine, and you square it. Remember the, I guess, problem number 13? Yeah, the polarizing filter thing, right? The same thing applies here. The intensity of this particular beam in this polarizing filter area is cosine square of theta. So if you want to measure the probability of this existing in this space, it will be cosine square of this theta. But if you want to measure the probability of this in this space, it would be, this was 90 degrees and this angle is 90 degrees minus theta, or phi by 2 minus theta, isn't it?
Yes.
So then this would be cosine square of pi by 2 minus theta.
Cosine square of pi by 2 minus theta.
Yeah. So I'm keeping the cosine square constant because I want you to look at the angles. Angles are more important here, and this will help you solve the problem.
So cosine squared is which part again? Just originally from that theta,
Cosine, yes, originally from this theta.
like the bottom.
So if instead of theta, I wrote this angle as phi, right?
Yeah.
That should be cosine square of phi. That would be the probability of this existing in this space, existing in this basis, basically. Okay. And this is what we call as a measurement. The probability of measuring this phi in one, because our measurement is restricted to zeros and ones. We are not measuring phi in some kind of a weird plane in this angle. We are only able to measure zeros and ones. The probability of this existing in one is just this
So
cosine
I'm trying to
square.
measure like the probability of the state of psi being either 0 or 1,
Yes,
similar to how like the collapse, right?
yes,
Is that
exactly.
kind of how this relates to QM in that way?
It does, yeah.
Okay.
So when you
Interesting.
collapse something, it's nothing but measuring it in that axis. Okay. So now you observe the angles, right? So the angles are important. Whatever you are measuring against, you take the angle of that between between your vector and that particular axis, and you cosine square it. You get the probability of that particular vector in that basis.
So if we took cosine squared of theta,
Mhm.
that would tell us between state 0 and state psi, or state. Yes.
Probability of psi existing in state 0. So psi can also be written as cosine of theta times 0 plus cosine of pi by 2 minus theta of 1, because this is my 1. Remember, you need to square these to get probabilities.
How much of that is cosine squared of theta?
How much of this?
Like is cosine squared theta from like below psi to 0?
Theta is this. Cosine square theta is this much. This length is cosine.
Got it. That's
No,
what I-
this length is cosine theta. So this length is this, but cosine square theta gives you the probabilities.
Okay. Yeah, that's right. That's why like it's like the amplitude very squared to get
Yes.
probabilities.
Yeah.
Why is that? Is that a big question?
Not really. It's. Do you remember the double slit experiment
Yes.
where the heights added up? So this is heights adding up, but your intensity does not add up. Intensity needs to be squared first.
Okay.
Same thing. We'll come back to that anyway.
Yeah. So we just know that cosine squared theta is how we get the probability
Mhm.
of psi going down to state 0.
Yeah.
Okay. I got that. I'm gonna write that in actually. The probability. That's probably why you said that. I want to know this in stats. Probability.
Cover it later. But for now, I'll cover the intensity part later. But for now, we know that
Yeah, I didn't really understand the intensity in the like problem 13 still is confusing.
intensity things.
Yeah.
Okay.
We
Okay.
talked about that with like is that with like the bullets and the
Yes.
waves? And we said like the bullets is like
Yeah.
the same, but one of them you like square it. Yeah.
This was the problem. If you have a slit like this, it doesn't matter how big the slit is right now. It just what matters is whatever you're sending through the slit is in comparison to the thing you're sending in. For example, if you're sending a bullet of half a centimeter diameter,
Mhm.
this would be in that order, like maybe 0.1, maybe 1 centimeter. 0.1 it doesn't go through, maybe 0.5 to 1, maybe 1 to 4, but definitely less than 10 centimeters. Basically, the order matters. And if you're sending in bullets through it, so this is your counter. If you send a bullet in, you're going to find a bullet here. You send a bullet in again, you're going to find another bullet here. You're always going to count bullets here, right? So your intensity would look something like this. If your bullets are coming in straight angles, like straight arrows like this, you'll find bullets intensity going up and down like this. You're going to measure some stray
Oh yeah,
bullets here.
so like obviously in the middle of it straight ahead. That's why it's the highest point of intensity. You're gonna find those bullets there, and then when it strays out slightly, just like the probability becomes less and less, right? That's
Yes.
why the curve.
Think of it like stray bullets going here and there.
Yeah.
And another important thing to note here is that the bullets that are coming in a straight lines. So basically, they are being fired from a very far distance. Okay. Not really that important, but it's very important for physics. Okay.
And so the weird part of the double slit is that light did that and created that same interference pattern.
No, light did not do that. In fact, light was thought of as bullets, right? So light should have created that, but it did not. Light created an interference pattern just like waves. If you send in waves, right? Now waves are emanating this way.
So
We draw waves like this because
is that what we're talking about? Water would be like
yes.
how okay.
But remember this thing: if your water waves have this thing called a wavelength. Wavelength is nothing but
Is that different than wave function?
they're kind of related because wave functions also have wavelengths, but I don't know how to answer that because they are used together, but they're not really the same thing.
Okay.
Think of a wave. This is a wave, right? This length is called a wavelength, nothing else.
Yeah.
That's it. So this just keeps repeating. This goes and goes and goes. Similarly, when just like you said, you have a water body and you ping it, you have these ripples created. Those are the waves. The difference is if you have a water body here and you create a water body and you created a ripple here, it just goes out in circles, right?
Yeah.
But if you're far enough here and you have only this much amount of a detector, you notice waves coming in almost straight lines because they're so far away, like circles keeping on going bigger and
Yeah,
bigger.
like that.
Yeah.
Like even more. Yeah.
So it'll be almost like straight lines.
Oh, okay.
If you're far enough.
I never thought about it like that. Yeah.
Think of it like Earth. Earth is round, but you can see ahead and you can see things that are you can still lay a flat piece of plywood or flat piece of cardboard and it still looks like it's flat on the ground, but it's technically curved a little bit. But
Yeah.
to you, it looks like flat. It's same thing.
Yeah.
If it is big enough, it's long enough and it's far enough, the waves at this end almost come like straight lines, like that, just like that. Okay.
So what you drew there is like maybe like later on of the wavelength.
Extremely later on, yes. So I'm going to assume that those waves are coming in like this all the time.
Yeah.
All parallel. And again, this thing applies. This length of this slit is comparable to the wavelength of this wave, right? And the problem was if it was water waves, you would have seen this kind of a pattern generated. I don't have a different marker, but I'll just erase the one below. It's because of something called constructive and destructive interference in waves. What happens
Like
is
when they cancel each other out, right?
Correct.
Like the trots.
Yeah. So, okay, you know about it.
Yeah.
So because of constructive and destructive interference, you get a pattern like this, right?
Why is it still the most in the middle then?
It's because all the energy comes in this one.
Oh, okay. So it's like
So you're going to have new patterns forming here. You're going to have new patterns forming here. And ultimately, at this point, you have a lot of amplitude. And as you go away, the energy of this guy coming here diminishes. The energy of this guy coming here diminishes.
Okay.
So even if it is a wave, right, it's slowly going to lose its energy as it goes far and far away. The
Yeah.
intensity decreases. Basically, that's what we say.
So the weird part was that.
The weird part of that,
Quantum.
light was thought of as a particle, so it should have demonstrated the bullet kind of pattern,
Mhm.
but it demonstrated this thing.
Wait, okay,
So
it's all the same.
yes,
Okay, that makes sense now. I never thought. Usually, I'd see the waves,
Mhm.
and like I got by just understanding that it functioned like a light
Mhm.
or it functioned like a wave,
Mhm.
and like how that meant that it was not supposed to do that, but it helps understand like why the waves are like different heights and such, and like what that means from
Yeah.
that experiment.
so if you want to take a little bit of tangent there, this almost demonstrated that light is a wave, right?
Mhm.
Perfectly. It's like you're sending in particles of something and you're seeing that pattern. That means light must be a wave. But here's the interesting thing. If you have you heard of the photoelectric effect?
A little bit, yeah. It's a discrete. And I said that like light lives in like discrete packets, right?
Yes. Why?
What exactly is discrete? I know you can write a book about that, but
So it says that light moves in terms of packets of energy. So here's what happened. Early in Newton's days, this was around 1600s, late 1600s, maybe 1650s or 67s when the Nature was published. And so when Newton published it, he said lights are particles. Everybody thought lights were particles. And
Yeah.
then at the end of around 1800s or maybe beginning, whenever Huygens was arrived, his name, I don't know how to say his name, I just call him Huygens, Huygens.
Mhm.
All right. So this guy was alive around 1800s or so, somewhere around 1800s. And he said basically that light is a wave. And using his theory, they basically made this theory of electromagnetic radiation, which is light. And then there were like 4 amazing laws in physics that were formed. They were labeled as Maxwell's laws.
I don't know this.
That's fine. It's not important here. There's a lengthy derivation, and what you mentioned as wave function, right?
Mhm.
It came into picture there. So they used those to determine 4 basic functions of electromagnetism in terms of electric and magnetic fields. And then, so then they conclusively proved, basically saying that Newton was wrong and we have waves alone. We don't have anything else. But then Einstein came back in 1900. So imagine what the period is like. 1660s, Newton says they are particles.
Yeah.
1800s, people say they're waves, and 1900s, Einstein says they're particles. And right now we say they're both. Because they couldn't figure it out. Or they could, we just don't know. Because light did both. Light performed the photoelectric effect as well.
Yeah.
So basically you bombarded a piece of metal with light,
Mhm.
and at a certain energy, you were able to see knocked off electrons and knocked off photons. That is only possible if you have light in terms of particles. So anyway,
But at the same time, it forms the wave interference.
yes,
Okay.
it does the interference, it does the electric effect. It also, well, technically it's not. No, that's electrons. Electrons do something. So anything in that order, right? So there's something called Planck's constant, which is at the
Yeah.
order of 10 power minus 34. And electrons exist in the order of, not electrons, atomic radius exists in the order of 10 power minus 10. And nuclear radius exists in the order of 10 power minus 15. But anything that is, anything that has to do with electrons, right? It's so small that it also behaves almost like a wave. That's why we use electrons and light interchangeably in many places. So,
That makes sense.
and
Context.
here was the most amazing discovery they made. Light, they observed this in light, which made sense, right? But we knew that at that time electrons had to be pieces of balls, or basically in early 1910s to 1920s, right? All the theories said that electrons were pieces of balls that were rolling around nucleus.
Yeah. Like the old Bohr's model of the atom, right?
Bohr's, Rutherford's.
Yeah.
They had so many theories.
But a bunch of different ones, right? Yeah.
Yes. But then they proved it, they showed it that electron also did this. Electron also had a wave nature. So they basically bombarded electrons one by one.
So
through
now
this
it's just
jet.
like the cloud, right?
Yes.
Yeah.
So now we don't know what it is. And then there was this experiment called the Compton scattering. Compton, I think it was at 1900, somewhere in 1900s to 1950s. I'm not sure exactly when, but it was between World War I and World War II. He did this experiment where he basically, so they proved that, so this was kind of a blow to the electron as a ball community, because they said, since electron is a ball, it should not have exhibited that behavior, isn't it? But
Yeah.
electron did exhibit that behavior. And finally, then Compton put up, there was another gold foil experiment where they bombarded a lot of electrons again on an atom, but that had nothing to do with electrons on its own. The kicker was Compton placed a piece of metal in the center and bombarded electrons at one end. Okay, so based on certain angles of the metal, you found a peak like this, which was obvious at the end, but you also found another peak at some angle here or here based on the metal that was placed there. So here's what happens. An electron comes in, it hits an atom, and it emits a kind of radiation, some energy, and then it either absorbs or it releases that electron.
Is
as
that
well.
splitting it or is that different?
It's not splitting it. So it's going to hit an atom, and these atoms are tightly packed. And if the energies match up, right, there's a certain amount of energy release that we know what the energy is about. We know what the energy is going to be. But it exhibited some kind of a scattering behavior. Basically, they had a peak like this. They had two peaks. They were expecting one. So
From shooting an electron to the atom.
Yeah.
So just like one peak, there's two
two
different.
peaks. So kind of behaves like a marble. You hit one, and then it has an elastic scattering. There's something, okay, I'm going too much detail, too much into physics. And there's elastic scattering, which is observed in balls. So elastic scattering is like billiards balls.
Yeah, so like it's in the right?
Yeah. So that was the only explanation they could give. But anyway, the point is electrons and photons behavior are similar.
Electrons and protons. Is there some-
Yeah, photons is nothing but the unit of light that we call photon. Anyway, so according to wave theory, according to that one, the heights of these waves, right, they add up here. So that's
That's
causes
why
this
that's the
height.
highest one, yeah.
That's why we call, so we can call 0 as a height, 1 as a low point, and we can call the probability of it existing in this one, probability of it existing in this particular high or low. These are discretized points.
Would you say 0 is high or 1's high?
It doesn't matter. We can pick.
So 0 for my brain. For my brain right now, I'll say that 0 is low and 1's high.
Yeah.
So then that means that you're saying that the cosine theta,
Yeah, it's the probability of it being found.
right?
You can imagine like there's a theta here against this. But what angle will you find? What kind of a probability?
Okay, so it's not always like the probability of that the apex. It can be like different.
Yeah, but this is not an exact thing, and this doesn't exactly match to this, but this is just an analogy I'm taking.
Yeah.
Right.
So like the cosine theta, like in one spot on our probability,
Mhm.
let's just say like a point on there, it could be any of them.
Yes.
That's what cosine theta is trying to find.
And the probability is not cosine, probability is cosine square.
Yeah. Yeah, okay.
It's just the amplitude. The probability amplitude gets added up, but the probability itself has to be squared.
And you can relate that to, that's why you're showing me that. in
Yes.
terms of-
This is why the
It could be
double
any of the
slit
points
experiment was important.
on the count, right?
Ah.
So you're saying that that's why it's important.
Yeah, double slit was important because you can relate a lot of wave theory to a lot of this quantum phenomena.
Okay.
Big tangent. So the point was, if you have a wave, don't really relate that to here right now because this is more
Yeah.
geometry and
Yeah.
that is more physics.
So it's like a larger scale.
Yeah.
Relate, okay, yeah.
And this is my wave function right now, or this is my, what do you call this?
Wait, what?
State.
State,
Yeah, this is my state right now, and I want the probability of this state existing in this particular thing. So I'm only able to measure zeros and ones. That means if I have a wave like this, let's say I have a wave like this, I'm only able to measure highs and lows. That's it. I'm not able to measure anything in between. What I'm going to say is, if it exists somewhere here, right, I'm going to say it's one. If it exists somewhere here, I'm going to say it's zero. Let's say this is one and this is zero, right? But it still exists here. So there's some kind of probability that it's going to come down. So there's some kind of probability it's going to go up.
Depending where it is on that, yeah.
Yeah.
Okay. The probability that state psi will be at 0 or 1.
Mhm.
So the probability that will be at state 0 in that case would be cosine squared.
Yeah.
Okay.
So it all depends on how much of an angle that particular point is making with my state, with the basis vectors, and that's the probability that I'm going to measure it here. Okay. And by the way, that thing was a probability plot.
What is that?
This thing plotted there.
Oh, okay.
That's,
Yeah, you just already plotted the cosine there. Okay.
anyway, that part is clear. So let's jump into measurement one.
Probability of psi of like 2, 0, then I guess that way is the way to think about it.
Come again.
Like the probability of state psi relative to 0, like a probability that it collapses, right?
Collapses to zero.
Yeah.
Is cosine square of theta.
Yeah.
Correct. But here's the thing. I labeled this as 0. I labeled this as 1. I could label this as u, and I could label this as u perpendicular. It wouldn't make a difference. The probability of phi existing in u is cosine square of theta, still cosine square of theta. It doesn't change.
No
Probability
matter,
of,
no matter how long or any of the direction of state psi, it'll always be cosine because of the axis, right?
yeah, but
The basis.
the more important point is which basis. What are you labeling this? If you are labeling it u, so the probability of this existing in u is cosine square of theta. The probability, if you label it as 0, this the probability of psi existing in 0 is cosine square of theta. So it's very important that you know two things. One is what basis it is and what angle it is making.
Does it make sense to say, because we're saying like the probability of state psi existing in,
Correct. So it's like
is that like when you see like is an element of and you see that like notation that kind of looks like an E? Is that kind of related to probability?
this.
No, it's like a parenthesis and then a line in the middle of it. That's how I describe it. You described it as something earlier, but I'm thinking of this.
Oh no, that means belongs to. That has nothing to do here.
Nothing to do with it. Okay. So
And that, okay, I'll just leave it at
Yeah.
belongs to for now.
yeah, state psi existing in state. Yeah. Okay.
So the two things that you note here was whatever angle it makes with my basis vector, it could be any basis vector, it doesn't matter what it is. It is cosine square of theta, and with the corresponding perpendicular basis vector of it, it makes cos minus pi by 2 minus theta square.
And the pi by 2 comes from,
Pi by 2 is 90 degrees.
Okay.
because this is 90 degrees. So this is theta, this must be 90 minus theta,
Yes.
right? So anyway, these 2 points are very clear. I will go on to here. The states that we have exist in U and V. That's it. They don't exist in any other state. So my basis vectors are always U and V. But the catch here is U and V are not perpendicular to each other. Okay, it doesn't matter. I want to calculate something called probability of success, which is defined as 1/2 probability of U plus 1/2 probability of V.
Says.
Yeah, I'm not sure if it is an official definition. For now, the problem
what
states
is
it,
P
but
U P V?
it could be. It could be. It could be an official definition, but I'm
No,
not
I meant
sure.
like what is P U P V?
I'll tell you. So the probability of
Oh, U. Oh,
U, yeah. So if I take any basis vector,
in this case, U and V, right?
Yeah.
Our basis.
I take any basis, let's say A and A dagger. So they are perpendicular to each other, always, isn't it? A and A dagger have to be perpendicular to each other.
Yeah.
So here's my claim. Probability of U existing in A, right? The probability of U, this is how they defined it. Probability of U being U.
Being
Yeah.
itself.
Yeah, but
Okay.
in that basis, in basis A. So if I had a U vector like this, U like this, and A dagger existed like this, what do you think the probability of U existing in A would be?
Cosine squared theta.
Exactly. That's what P of U is.
That's what P of U is saying.
Yeah.
1/2 P of U.
Mhm.
Let's try to get 1/2 P of V. The fact that this is theta, and it's going to be cosine squared theta. I'm just going to draw a little arrow to P to that. Okay.
And similarly, if you replace U with V and you have the same theory, it's again going to be cosine squared theta. But they state very explicitly, let's do the first part of the problem. They state very explicitly that measurement 1 means you measure the basis U and U perpendicular, and you say if the your measurement basis is this thing, U and U perpendicular, these two. Okay.
Yep.
So the idea is if you're measuring U and U perpendicular, basically if you're measuring U in terms of U and U perpendicular, what is the probability of U? What is PU? What is the angle between U and U itself?
You say it one more time.
Okay, so I'm measuring a vector or a state U in
Would it
this.
be like what's listed here, since it says measuring the basis and this is U equals that?
Yeah, so if I'm measuring and
Is that our new cosine squared theta, or is that not how that works?
no, it is cosine square theta, but I want you to understand what theta is here, because that will be the value of P of U. So right now, this is what P of U is saying, is equal to cosine square of theta plus sine squared. If the outcome was U, then guess that the qubit was in state U. If the outcome was U perpendicular, guess that it was in state V. Basically, if you measured in the U and U perpendicular state and you got that your outcome was U, that means you're saying that you're in state U.
Yes.
But if you measured and you got U perpendicular, that means you're in state V. That's what it says.
Okay.
But what would be the probability of U being in U? because the angle between u vector and itself is 0. Right? It doesn't make any angle with itself. If you have a vector here 0, it's similar to saying what's the probability of 0 existing in 0?
Yeah,
It's just 1. Because
the probability of something being itself is 1.
is 1. Yeah. So then probability of u is 1.
Okay.
Because if you measured
Oh,
u,
okay. 'Cause
right?
It's just saying like, what is the probability that U is itself,
yes,
right? So there's 100% probability.
yes, exactly.
What it is it.
Yeah.
If we're defining it as it.
Yep.
Okay.
So one part of the problem is into 1, and then we need to measure the probability of v.
Let me just write in probability of U being itself is 1. Is it abstract? Or are we just preempting that to understand what we're about to say?
No, it's going to ask a question, and question is what is the probability of success of measurement 1 as a function of x? So probability of success is defined as this thing. That's why we are trying to calculate P of u and P of v. So basically it's saying P of u is if you decided that you are measuring along a
Oh, so we're saying probability of U, we said that was 1. Then you say
Yes.
that's 1, so
Yes.
just 1/2 plus whatever we figure out B.
yes,
Okay, so that's like the first half of the
Yeah.
answer, right?
first half of first part of the answer.
First part, okay.
Don't worry, it will be quick.
Okay, yeah. So then probability of B.
Uh-huh.
Is that the probability of V being itself? Or no?
The probability of v in u perpendicular, because your basis
Oh.
is u perpendicular now.
Oh, okay. Right, so it's not like if that was P U perpendicular, we'd also say 1, but in this case it's not.
Yeah.
So we're gonna say. Okay, and that's why they give you the pi minus 2 minus x.
Yeah.
The math there. We didn't need that before for U.
Think of it this way: you had that curve, right? You have this kind of a wave, and you said that this was u and this was u perpendicular, but the problem was your state exists in u and in some state maybe here and not there v. You decided that if I got u, I'm going to say it is u. If I got the state u, if I measured this state, so there are two possible states u and v. If I measured this system and I got u,
Mhm.
I'm going to say it's u because that's what I decided it to be.
Yes.
And then if I measured v, I'm going to say it's sorry. If I measured u dagger or u this thing,
Yeah.
I'm going to say it's v. These are the only two states my system exists in. This is not a official state. This is just something I made up. Right?
Mhm.
So that's the thing. If you want to measure v in terms of u dagger, you just need to check this angle and cosine square it.
Was the pi?
Which one?
Where'd you get the pi minus?
Oh, ignore this
I-
one now. I'll come to that. But
Oh,
you do
okay.
understand that this is the angle I need to
Yeah,
measure.
that's
right?
like cosine squared.
Cosine square of this
Theta.
angle. So this is my state and this is my basis. So if I want to calculate the probability of this state existing in this basis, it's just cosine square of this angle. So my
Yes.
probability of success of this state being in this state in this basis is going to be cosine square of this angle. Similar to this thing.
Yes.
So
So the probability of V existing in U perpendicular is cosine squared theta.
and theta being the angle between v and u perpendicular.
Yes.
So now I want the angle between them, which is very simple because this is perpendicular, this is u and u perpendicular, so this has to be 90 degrees, right? And I want this angle. I know that this part is x. This entire thing is x.
Yeah,
Because
the entire
this
thing is X.
it's
Yeah.
x by 2 is totally x.
Yeah.
And this angle will be 90 degrees minus x.
Oh, yeah, from the,
So I just
so
replaced
all of this, I'm just gonna point arrow to that, that's 90 degrees minus X.
Yeah. right? So this is 90 degrees minus x. So the
That equals cosine squared.
cosine square of 90 degree minus x. Because I need the angle between these two. Cosine
Oh, so
square of-
that is our angle. Are we saying that pi over 2 minus x is our theta?
yes, it is.
Okay,
It is r theta because that's the angle that this vector and this
because we're
vector
trying to
makes.
find theta.
Yeah.
We said that whole thing between v and u perpendicular is
Uh-huh.
cosine squared theta.
Yeah.
And because they gave us that other side, we know it's 90 degrees, so we can know for sure that x. They gave us that,
Mhm.
that the rest of it would be 90 minus that.
Yes,
If we don't know what that is, we say 90, I guess, or pi over 2.
pi
Yeah,
over 2.
pi over 2.
90 degrees is same as pi over 2. Right, so
Okay.
that will be my answer. My answer will be finally 1 over 2 plus 1 over 2 cosine square of pi by 2 minus x
What's the answer?
for the measurement one.
How many are there?
There are two measurements.
2 minus x.
Yeah.
So that means that answer for measurement 1.
Mhm.
1/2 plus 5 over 2 minus x.
The next measurement that so this is measurement 1 and 1.
Yeah.
And I know that my M2 is measured in standard basis 0 and 1. Note that I didn't care about, I didn't really care about how they have worded my state. They have written some very long states like cosine of pi by 4 minus x by 2 and sine of pi by 4 minus x by 2 is u and all that. It's going to be important when you do algebra, but when you're going to do geometry, it's just the representation that counts. If you can represent that in these terms.
Wait. So. Okay, so if it's saying that pi over 4,
Mhm.
which
This
my
is
brain is also. Yeah, okay. Okay, so does it make sense to say that between u and v,
Mhm.
that if that's x over 2, then that's all of x. So therefore. Could we say that, let's see, pi over 4. It's like 180, 90. So that's 45.
Mhm.
So that means that the rest of it, after the dotted line, it's 3 pi over 4, right?
this one.
After the rest of it. So that section of, like, okay, like if I'm seeing this,
Mhm.
I'm saying that this is pi over 4 and this is 3 pi over 4, right? Or no, I mean whatever gets us to. No, this makes sense. No, because it's not.
No, think of it.
I'm trying to think of. This is pi over 4, then this is also pi over 4, right?
Yes.
Will that help us or
For what? The next problem or this
Yeah.
problem?
either one?
No.
Okay.
I told you. The most important things are what you're measuring and what your basis is.
Okay.
That's all matters. Now, this is not one of my bases or my measurements. So I don't care about it. This is not one of my bases yet.
Yeah,
It's going
right
to
now just 0 as to.
Yeah.
To you.
Yeah, you can in fact do this. Draw the diagram, ignore this part, ignore this part completely.
Even you, or I mean even 0.
Just keep u, v, and u perpendicular, and make a note of what these angles are, and you'll have better success.
Okay. So now we're just thinking UV and U perpendicular?
Yeah.
Are we still doing measurement one?
No. So measurement one is done. That is the answer for measurement one.
Measurement two, measuring the standard bases, interpret state zero as state U. And then it's one state B. So why are we ignoring zero then if that's,
No, now we're going to bring back zero because they wanted to interpret in zeros and ones. That means my basis is now 0 and 1.
oh, is that like when they said, measure the standard basis and interpret zero as U.
Mhm.
That's the first part of measurement two, okay. So now we're just worrying about zero and U then, right?
Right now, 0, U, V, and 1. That's it. Because 1 is perpendicular to 0, and that's one of my bases. So the problem says if I measured 0, I'm going to count it as U. And if I measured 1, I'm going to count it as V. Okay, right? That's what it says. So if I get a 1, I'm going to count it as V. That's what it says.
Right.
So I need to calculate my probability of success, which is nothing but I need to measure this angle and this angle.
So that they can get there basically, right? So that one is the mean, your
Yes. So this angle would be, this is what, pi by 4, this is x by 2, this should be pi by 4,
minus x over two.
correct. And then this is also pi by 4, because
So to the dotted line
Mhm.
was pi over 4. And then to the from 0 to U is pi over 4
Mhm.
minus x over 2.
right? And what would this angle be?
What do you think? So
This is not important. I'm going to give you 2 hints. This angle is pi by 4 because this was pi by 4.
Yeah.
This is 45, this is also 45 because 45, 45 makes 90, and this is a 90-degree thing, 90-degree basis.
so it'd be pi over 2 minus,
This is pi by 4, but this part is x by 2.
oh, so we're combining some sort of, okay, I need the order, I don't know the order yet, but I know it's
It's
gonna
fine.
involve pi over 4 and x over 2. So I'm gonna say that it's gonna be the whole thing between 1 and pi over 4.
Mhm.
Would it be pi over 4 minus x over 2?
Perfect.
Oh, the same thing.
Yeah.
Okay.
So now you know the angles. Now you know the angles, you know how to do P of U and P of V, which is cosine square of pi by 4 minus x over 2 plus half of square of pi by 4 minus x over 2. And the total sum is cosine square of pi by 4 minus x over 2.
Cosine squared of our p probability of success to measure 0, the u existing in 0,
Mhm.
which is pi over 4 minus x over 2.
Yep.
Then we're adding that with 1/2 as the probability of v existing in 1. Right?
Mhm. Yeah.
Oh, I wrote it in the wrong place.
That's fine.
I wrote I wrote it between V and U, so I just kept looking at that. I was like, that's not right. Okay, here we go. So that's here. That's the pi over 4 2, so that's 5/4 minus x/2. And so it's just, yeah, so that equals. Forgot the other cosine squared. So cosine squared, so that means it's just cosine squared pi/2, or pi/4 minus x/2.
Yep.
That's the answer to the second measure.
Yep.
Okay.
The last one.
Now note that the following.
I'm going to erase this one because it's not important for the last one.
Question.
I'm going to erase this one because it's not important for the last question.
What?
So problem C, right?
Yeah.
It's not it's not important. This part is not important for it.
Okay.
So I'm going to just erase it.
Okay. This. So. What's a fraction? 2. Plus. Plus. Plus fraction. 1, 2. Parentheses. Do I have to do like /frac, then /pi if I want to do pi/2?
Forward slash. Let me see. What are you trying to do?
I'm trying to write 1/2 plus 1/2 within parentheses.
Mr. Cos. That part, this part. Mr. Cosine squared here.
Yeah. So where would I put the cosine? Oh, okay. 1/2 cosine squared. Right. Cosine squared. Yep. So then that's. I'm going to do 1/2 plus. Cosine. Then parentheses. But I put the fraction part in first, like with that.
Yeah.
Fraction, and then another one for pi.
You have to put them in brackets like this fraction.
But which part, right? The pi?
Yeah, whatever is on top has to come in. No. You need to put. Okay. So the fraction has two parts, right? There's something on top, there's something in the bottom.
Mhm.
The part on the top is put in the first curly braces, and the part on the bottom is put in the second curly braces. So the first curly braces, you put pi in there.
Oh.
Or pi/2. Oh, wait, yeah, pi is fine, and then you put 2 there, and then you put a minus, and then x.
That answer for measure 2 was.
I'm not sure if probability of success is a real thing.
General. squared. Is I see. That helps me think about where to put these. But hard to see, which is irrelevant to what we were doing earlier. Now note that the following become good approximations as theta to 0. Sine theta is around approximately theta. Sine squared is 45 minus theta is around 1/2 minus theta. Use these approximations to estimate the probability of success of the two measurements as x to 0 and as a function of x.
Okay.
So those are our two measurements.
Yes.
Sine theta is, what would you call that exactly?
Which one?
Between sine theta and theta, you see that's like, what's the English for that, I guess?
The sine theta tending to 0.
Tending?
Oh, okay. The arrow, the forward arrow, you write that sine theta or as theta tends to 0. You write sine
Oh,
theta
no, I meant
tends to
below
0.
that.
Yeah.
With the wavy lines.
Yeah, so you can call it as tends to 0 or tends to theta. So it's
Tends to
like
theta.
you read it from the theta tends to 0, sine theta tends to theta.
Does that have anything to do with the tensor? Or is that literally?
No, the
completely
tensor,
unrelated?
there are no tensors here.
Completely, okay.
I don't think there are tensors even till assignment 2. Even in assignment 2. Not sure, but don't think so.
So sine squared. of 4 times half minus theta. Okay. So I'm just gonna write out our equation. 1/2. So for this first one, sine theta,
That's not important. But the question is, use these approximations. You don't have to solve sine theta tends to 0. That's not a question.
Mhm.
That's just some information that they have given you. Use these approximations to estimate the probability of success of the two measurements as x tends to 0 for a function of x, right? So if you replace x with theta, you can say in the above case as x tends to 0, sine of x tends to x. Because if sine of theta tends to theta, sine of x will tend to x. No, not yet. It's close by. But the question is, if you use these approximations and estimate the probability of success of the two measurements, which measurement would be more appropriate? Basically, it's trying to say, you have these two measurements, M1 and M2, isn't it?
So that means
You have two measurements there, M1 and M2.
Yep.
Right? You use two different bases to measure the same two states.
Yeah.
The states are still U and V, they don't change. What changes is how you measure them. Right?
Mhm.
So using these two states, you try to measure, and now the question is, if that x in that measurement, the x in your equation, if that tends to 0, then which is a better measure, which gives you a better approximation? There are two things you need to note here, which is important for solving this. One is there's a if there's a inequality, I guess you can say inequality. So if x is less than 1 but greater than 0, something like 0.5 or 0.1 or 0.3 or 0.1123 or whatever.
Yeah.
Right? If this is the case, if x exists between 0 and 1 and 0 is included, then x squared is less than x.
Yeah.
Right?
Yeah.
And
The only time it'd be equal is if it was 1 or bigger.
yes,
Right.
equal or greater. If it is 1 or greater, it will be greater. And the second thing you need to note is cosine square of theta plus sine square of theta is equal to 1.
Yeah.
Right? So I can write sine square of theta is equal to 1 minus cosine square of theta. Right? So in the, let me make a brief note at a corner here. I'm going to say x is greater than 0, less than 1. This implies x squared is less than x. Right? I just wrote the same thing there. And I have this condition, sine of theta almost equals theta as theta tends to 0.
Okay, so you said that 0 is less than x, which is less than or equal to 1.
0 is less than x, yeah, correct. Not less than or equal to 1.
Okay. And that's all less than x squared. Less than x.
No, no. If this is the condition, if this is the condition,
Okay.
then x squared is less than x.
Okay, so if that top one, then yeah, so if x is less than 1,
Mhm.
greater or equal to or more than 0,
Mhm.
then x squared is less than x. Okay.
And you have this condition, right? Sine theta tends to 0
Mhm.
as theta tends to sine theta tends to theta as theta tends to 0.
Yep.
And also you have this thing called sine square of pi by four minus theta. It becomes 1 by 2 minus theta. This is given in the question.
Yeah.
If I replace this sine square with this cos square, it becomes, so I'm going to replace this, and I'm going to treat this entire thing as theta or x.
Okay, so you're just replacing that
Mhm.
sine squared with a 1 minus cosine squared to make it 1 minus cosine squared parentheses pi over 4 minus theta.
Yeah.
Is tends to 1/2 minus theta.
So I can write this as 1 minus cosine square of pi by 4 minus theta, which equals 1 by 2 minus theta, right?
Mhm.
I just replace that with 1 minus cosine square theta, which is nothing but I'm going to take one the other side. Okay, it become minus cosine square pi by 4 minus theta almost tends to 1 by 2 minus theta minus 1.
1/2 minus theta minus 1.
Which is similar to minus half and minus theta. Because minus 1 plus half is minus half. Calculate it here.
Wait, so we yeah, the 1/2 minus. Wait, it's negative now though.
Yeah, it's negative because minus 1 plus half, right?
Oh, okay. No, let me see here. I wrote negative cosine squared pi over 4 minus theta tends to 1/2 minus theta minus 1, and then we're adding another tends to.
Yes, because I'm going to combine these two. 1/2 and minus 1.
Oh, so 1/2. Yeah, okay, equals -1, so therefore, you can rewrite the whole, I'm sure rewrite the whole thing for me.
Sure.
Cosine squared, let's use pi over 4 minus theta tends to.
Mhm.
Yeah, -1/2 minus theta, okay. That makes
Right.
sense, yeah.
And now, since it is.
I thought you were saying there's all, you just like added that to the equation. I was like, wait,
No.
what?
And I take the negative out on both sides.
Mhm.
Right, so it becomes cosine square of 5/4 minus theta tends to half plus theta. So I basically removed the minuses on all sides, just made it plus.
It doesn't matter about the pi over 4 minus theta, that stays the same. Yeah.
This is inside cosine square, you can't
Yeah.
move negatives inside it. Not unless
That'd
it's
be
sine.
crazy.
No, I mean, if it were sine, we could have moved it, and if it were not squared, we could still move it, but it's
If it was
fine.
a sine?
Yeah.
Really?
Yeah.
Why?
This is theta, right?
Yep.
Now, this would be your sine of theta.
Yeah, cosine to the bottom.
Now, if you had minus theta, which is basically the same angle, it would be minus sine theta.
Oh, and cosine's like kind of the x-axis in that case anyway, in
Yes.
that example, so that wouldn't switch.
So if you have negative, it technically goes in,
So you can't do that with sine, but
Yes.
not cosine.
not cosine.
Got it. That.
So you got this part, right?
Yep.
Okay. I'm going to erase this part. Okay. So I know that cosine square theta tends to 1/2 plus theta. Let's say I'm doing measurement 1, which is this one, the one on top,
Mhm.
right? If x was tending to 0, right? This is pi/2 minus x.
You just take cosine squared of 5/2 then.
No. I'll change this cosine square theta to sine square theta,
Why?
because there's a. Wait, do I need to do that? Yeah, I think I don't need to do that. Sine of theta tends to theta, right?
Yep.
So sine square of theta will tend to theta square.
Yeah.
Right? That means 1 minus cos square of theta will tend to theta square.
So 1 minus cosine squared theta.
Mhm.
That's a cosine squared.
Well, this will get kind of complicated because I have to square them. I don't want to square that. Let's do it. The problem is if I take theta square, right, I have to square this, which will be longer. Because whatever is in here gets squared.
Are we still using measurement 1 for this problem?
We are. It is still
really?
measurement, yeah. I want to,
As an example, or as a part of the question?
it's a question now. 1/2 plus 1/2,
Oh,
Cosine.
of the two measurements, yeah,
Yes.
okay.
5/2 minus x, right? This
Yeah,
is my
yeah,
measurement 1.
Yeah, let me rewrite measurement 1 then. 1/2 plus 1/2 cosine squared
5/2.
over 2. Next to it. 2.
Right?
1.
So you know the pi/2 was 90 degrees.
Mhm.
Pi/2 was 90 degrees, right? And I have something like this, and I have this as x.
Yeah.
Right? So then this length would be
Cosine.
cosine of x, this length would be sine of x. Right?
Yep.
But I can also write this as pi by 2 minus x.
Yep.
So then this angle also becomes cosine of pi by 2 minus x. Because it's
Oh, okay, so we can say that,
we can say that cosine of pi by 2 minus x is same as sine x.
okay, so why do we have the cosine again?
Because that thing is cosine, I want to change that pi by 2 by x to sine.
I meant like in the, yeah, so cosine,
Cosine of this angle. So the vector still remains the same. I'm trying to project it here.
you're taking the cosine of that.
Yes.
Okay, okay. Got it. So then cosine of, yeah, cosine of pi by 2
Mhm.
Minus x
Mhm.
equals sine x. Okay.
Yes. So now you see the same thing. Cosine of pi by 2 minus x here in measurement 1.
Cosine squared, yeah,
I change it to sine x. Because
but it's squared, doesn't matter.
so here's what happens. When you take cos squared of x, it is same as cos of x whole squared.
Yeah.
This is just a notation. This is what really happens. People write it because this looks fancy.
Yeah.
It doesn't matter. This is what happens. Or there might be a reason. I don't know. I don't know that much math about it.
Okay.
Anyway, but I can replace this with sine square of x. So what I'm going to do is square on both sides. Simple.
Cosine squared of pi over 2
Mhm.
plus x equals sine squared x. Okay, so you're just squaring it then.
Yeah.
What you had from,
Yeah, I mean, I can square it, I can cube it, I can
Yeah,
put n into it, but it's still the same.
okay, just trying to. We have the axis and we have some line that is x.
Mhm.
Know that. In a 90-degree angle. We're gonna have,
It doesn't matter. If you see of the form
pi over 2 minus x.
cos of pi by 2 minus x, it doesn't matter what the angle is. If you see anything of this form,
Yeah.
you can replace it with sine of
Good
x
to know. Yeah.
every time. It works.
Is that just something you learn after doing it a while? You see it more and more.
Kind.
Do you see that commonly?
Yes, very common. It sometimes makes your life easy.
Okay.
You see how easy it becomes. So I can replace this with 1 by 2 plus 1 by 2 sine square pi by 2 minus x. Sorry, it becomes sine square of x now. Right?
Yep.
And I know that as x tends to 0, sine of x tends to x. Right? As x tends to 0, sine of x tends to x. This is given in the problem.
Yeah.
I just
Yeah,
replaced
just rewrite, yeah.
x with theta. So then I can replace this with x squared, isn't it?
Yes.
So this becomes 1 plus x squared over 2.
Okay. Yeah,
I just
because sine of
replaced
x
sine
is
squared with x
is
squared.
approximate, that's x. So then, yeah, okay.
And I'm going to do this part because I've already calculated that. Now I need to do M2.
Is that the answer then?
Yes, this part is the answer for M1. Then I need to calculate M2 and then compare them. M2 is cosine square of pi by 4 minus x by 2.
So let me try to. think about this. So.
Mhm.
Can we say,
Use this there.
we just say that it's 1/2 plus x over 2?
Perfect. That's what it is. So it becomes 1/2 plus x over 2.
Using, okay, I'm trying to find on my paper where I wrote that.
Okay.
Cosine squared. Oh, I see. Using, and then put an arrow to that, using that. We know that. Is that given the problem? No, but we got there from the sine squared stuff.
Yeah.
From the pi over 4.
Yeah.
So using that, we know now that 1/2 minus x squared plus x over 2. So the answer for that then?
For M2, yes. Now, so the answer for M2 is this one, the answer for M1 is this one. So the question is, do you remember that rule? If x is
Yes.
between 0 and 1.
Yeah.
Now, when you're measuring something, you want two different things to be as far apart as possible. For example, if you're measuring, let's say, the distance between two stars, right? If the stars are too close to each other, it's going to be really hard to measure whether the distance between them. If they're far apart, you can tell the distance between them easily. So the allegory is if stars
Why is
are
that?
uh-huh.
Even in space?
Yeah.
What? How?
If two things are close to each other, you need a really precise measurement. So basically,
Which is kind of what we're doing, right?
it's like, imagine there are 2 points here and there are 2 points here. If I told you to measure these two, to measure this, you need to get really precise measurements. You need to get extremely good scales.
Yeah.
And to measure this, you need basically any scale. It doesn't matter. You can get a ruler and you can start measuring. So
Okay. Yeah, I see.
further apart there, it's easier to measure them.
Does that apply on like a larger scale, like an actual star too?
Yes. If two stars are close to each other, you can't really easily measure them. There are too many things at play there, but that's the gist of it.
Okay.
Anyway, so the thing is, if you're measuring something, you want that the difference to be as big as possible.
The maximum, right?
Yes. So based on that, which one do you think is better, this one or this one? Remember that x is between 0 and 1. Yeah, take your time. That's the answer to problem C.
Measurement 2. I just plugged in 0.5 for x for me. And then I got 5/8 for measurement 1 and 6/8 for measurement 2.
Measurement 2 is the correct answer. So if you want to measure these two systems, the better measurement scale is measurement.
Because the question is saying. Now about the following, blah, blah, uses approximation estimate probability of success of the two measurements.
Of that, because X M1 is that, M2 is that, and that's the probability of success of those two measurements.
So for the answer to C, is it just answer two?